Hello, in this lecture we'll talk about the limit of a sequence. A sequence is a set of numbers, and a sequence can be finite, like the sequence, this sequence 1, 5, 7 that consists of only 3 terms, and a sequence can be also infinite, like the sequence of the natural numbers that consist of infinite terms. In this lecture we will talk only on sequences that consist of infinite terms. Okay, so the limit of a sequence is the value that the terms of a sequence tend to. Okay, and we write down that lim is abbreviation for limit of sequence a n. Here n is the index of the sequence. The index of the first term is 1, the second term, the index of the second term is 2, etc., etc., and a is the value of the term that its index is n. Okay, so here a1, this the sequence of the natural numbers equals to 1, a2 equals to 2, a3 equals to 3, a and the index n equals to 100, a of 100 is equals to 100, etc., etc. So the limit of sequence an when n tends to infinity, that is the way that we will write down that the limit of sequence an when n tends to infinity. So if sequence an has a limit, for example, the limit of sequence an when n tends to infinity equals to L, and here L belongs to the real numbers, it can be any real number. So here we are talking about a finite limit. So if sequence an has a finite limit that is equals to L, then sequence an converge, and you can say that sequence an is convergent sequence. Okay. A sequence that converge must have only one limit. That is to say, if a sequence has two limits, it means that it doesn't converge at all. So if a sequence Bn doesn't converge, then we will define sequence Bn as divergent sequence. So the limit of a sequence is said to be the fundamental notion on which the whole of mathematical analysis ultimately rests. So what is actually the definition of the limit of a sequence? Actually, a number L belongs to the real numbers. A number L is the limit of sequence AN when n tends to infinity. Only if the numbers in the sequence become closer and closer to L. I repeat again. Only if the terms of sequence AN are becoming closer and closer to the limit L when n tends to infinity, only then we can say that the limit of sequence AN when n tends to infinity equals to L. Okay? So only if the following condition holds, but before that we can write down that the limit of sequence AN when n tends to infinity equals to L. This is the first way to write it down, and a second way to write down the same thing is AN with a right arrow that is equal to the limit L. So those two methods has the same meaning, that the limit of sequence AN when n tends to infinity equals to L. Or those two expressions have the same meaning, that the limit of sequence AN when n tends to infinity equals to L. So only if the following condition holds, we can say that the limit of sequence AN when n tends to infinity equals to L. The condition that must hold in order that the limit of sequence AN when n tends to infinity will be equal to L is as follows. For each real number epsilon that is greater than 0, that is to say epsilon is a positive number but it is as small as we would like. For each real number epsilon that is greater than 0, there exists a natural number capital N such that for every natural number n that is greater than capital N, we will get that the absolute value of AN minus the limit L is less than epsilon. So only if this condition holds, we can say that the limit of sequence AN when n tends to infinity equals to L. Okay? So what is the meaning of this condition? Actually, the meaning of this condition is that the terms of sequence AN are close to the limit L up to epsilon. So here I can show it to you graphically that if L is the limit of sequence AN when n tends to infinity, so here L is the limit. Actually, the environment of L starts from point L minus epsilon and ends at point L plus epsilon. Okay, so those two brackets, what we have inside those two brackets is defined as the environment of the limit L. I'll repeat again, the environment of limit L starts from point L minus epsilon, but the point L minus epsilon itself is not included in the environment, and ends at point L plus epsilon. But here the point L plus epsilon itself is not included in the environment of L. Okay? And the radius of the environment of L is equals to epsilon. Here is epsilon, and here also from L until L plus epsilon, we have epsilon. So here each term that is located inside those two brackets is the distance of each term that is located inside those two brackets is actually less than epsilon. Or as I already mentioned before, the terms of the sequence AN, most of the terms of sequence AN are close to the limit L up to epsilon. Each term inside those two brackets is close to L up to epsilon. And according to the condition that must hold, because of the fact that until the index n we have fixed indexes, it means that we will have made n terms of sequence AN that doesn't obey to this condition. But from the index n onwards, we have infinite terms that are located inside those two brackets, and they obey to this condition. Okay? I repeat again, from the index n onwards is from the index n until plus infinity. From the index n until plus infinity, we have infinite terms of sequence AN that obey to this rule. So in order that sequence AN will have a limit when n tends to infinity, most of the terms of sequence AN, or infinite terms of sequence AN, must be in the environment of L, or most of the terms of sequence AN must be located inside those two brackets. Infinite terms of sequence AN must be located inside those two brackets. That is the environment of L. Okay? So this sequence AN, we can say about this sequence AN that is converge to the limit L, or tend to the limit L. Okay. So symbolically, we can write down the condition that must hold as follows. For every epsilon that belongs to the real numbers and it is greater than 0, that is to say epsilon is a positive number, there exists, this is the sign of exist, there exists capital N that belongs to the natural numbers, and for natural number n, for any natural number n that is greater than capital N, we will get that the absolute value of an minus the limit L is less than epsilon. Okay, again, this condition must hold in order that the limit of sequence an when n tends to infinity will be equal to L. Okay. I repeat again that sequence an that has the limit L is a convergent sequence, and L must be the only limit of sequence an. Otherwise, if sequence an has more than one limit, it is a divergent sequence. It is not convergent at all. Okay? So, in the next step, I will present to you an example of a sequence that its limit when n tends to infinity is equal to 0, and we actually will have to prove that the limit of sequence an equals to 1 over n when n tends to infinity is equal to 0. So in order to prove that the limit of sequence an equals to 1 over n when n tends to infinity equals to 0, we have to prove that this condition holds. So here we are talking about the sequence an that is equals to 1 over n. Here, when the index n equals to 1, so that is to say a1 is equals to 1 over 1, that is actually 1. When the index n equals to 2, so the second term of this sequence an, the value of the second term is 1 over 2, that is 1/2. When the index n equals to 3, so we get the value of the third term, that is a3, it is equals to 1/3, etc., etc. When the index n equals to 100, we get the value of the 100th term, that is to say a100 equals to 1 over 100, that is 0.01, etc., etc. When the index of n is n, so the value of the term is 1 over n. So it is very easy to see that the terms of sequence an equals to 1 over n. When n increases, the values of the terms are getting of this the terms of this sequence are getting closer and closer to 0. That is the reason that we will assume that the limit of sequence an equals to 1 over n when n tends to infinity equals to 0. Here it is very easy to see that the value of the first term is 1, the value of the second term of this sequence is 1/2, the value of the third term is 1/3, the value of the other terms of this sequence is 0.01, etc., etc. So they are getting the terms of this sequence are getting closer and closer to 0. So we'll assume that the limit of sequence an equals to 1 over n when n tends to infinity equals to 0. So we'll have to prove that this condition holds, this condition holds, and in this way we'll prove that the limit of this sequence is indeed equals to 0. So the condition that must hold is as follows. Let epsilon be a real number that is greater than 0, as small as we wish, and let capital N be also a natural number, belongs to the natural numbers. So for capital N that is greater enough, we will get that for any natural N that is greater than the capital N that we choose here, we have to get that the absolute value of 1 over n minus the limit 0, or the absolute value of 1 over n minus 0 is less than epsilon. So that is the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity will be equal to 0. Okay? So here, what is the absolute value of 1 over n minus 0? Because of the fact that when you subtract 0 from anything, it doesn't change anything, we can cancel here 0. That is to say, the absolute value of 1 over n minus 0 equals to the absolute value of 1 over n. And because of the fact that n is a natural number, that is to say, it is a positive number. And 1 over a positive number, it is a positive number. But we know that the absolute value of a positive number equals to the positive number itself. For example, the absolute value of 5 is equals to 5. Therefore, the absolute value of the positive number 1 over n equals to 1 over n. And here the condition that must hold is that the absolute value of 1 over n minus 0 must be less than epsilon. That is to say, we have to prove that the inequality 1 over n that is less than epsilon, that this inequality is true. So here we will multiply this inequality by n, and we'll get that 1 is smaller than epsilon times n. In the next step, we will divide this inequality by epsilon, and we will get that n is bigger than 1 over epsilon. That is to say, the condition that must hold is that actually this inequality must be true. Okay, so we have to choose such capital N that will cause this inequality to be true. So we will choose capital N that is greater than 1 over epsilon. So, and for every n that is greater than capital N, so here we will also have the right to choose n that is greater than capital N, and we already choose capital N that is greater than 1 over epsilon. Okay, so this inequality n that is greater than capital N, it is true because we have the right to choose n that is greater than capital N, and we already choose capital N that is greater than 1 over epsilon, so this inequality is true. From this inequality that is true, we can derive that n is greater than 1 over epsilon. Actually, we proved that if we choose capital N that is greater than 1 over epsilon, then we will get the inequality n is greater than 1 over epsilon. It is indeed true. So actually, in this way, we actually proved that if we choose capital N that is greater than 1 over epsilon, then this condition holds. So this condition holds. Okay? And for that reason, this will actually prove that the limit of sequence an equals to 1 over n when n tends to infinity indeed equals to 0. Why? Because the condition that must hold here, this condition indeed holds if you choose capital N that is greater than 1 over epsilon. Okay? So, as I already mentioned before, we have the right to choose n that is greater than capital N. That is to say, n is greater than capital N according to our selection. So this inequality is true. Here we will divide this inequality by n, and we will get that 1 is greater than capital N over n. Here we will divide this inequality by capital N, and we will get that 1 over capital N is greater than 1 over n. So this inequality is true, therefore this inequality is also true. That is to say, 1 over n is smaller than 1 over capital N. Okay? So here we have already proved that the absolute value of 1 over n minus the limit 0 is equals to the absolute value of 1 over n. And we have already proved that the absolute value of 1 over n equals to 1 over n. And we just right now proved that 1 over n is smaller than 1 over capital N. So we can write it here. Again, 1 over n minus 0, the absolute value of 1 over n minus 0 equals to the absolute value of 1 over n. And the absolute value of 1 over n equals to 1 over n. And we just right now found out that 1 over n is smaller than 1 over capital N. So this inequality is true. Okay? And here we'll focus on this expression 1 over capital N. This expression will be smaller than 1 over epsilon. Why? Because if we have the number 1/5 and we will decrease the denominator, we will leave the numerator as it is. We have in the numerator here 1, but we will decrease the numerator from 5 to 4. The original number will be greater. That is to say, 1 over 4 will be greater than 1 over 5. That is to say, you can conclude from this example that when you decrease the denominator, the number itself increases. That is to say, here we choose 1 according to our selection. We actually choose capital N that is greater than 1 over epsilon. That is to say, 1 over epsilon is smaller than capital N. That is to say, here we decrease the denominator from capital N to 1 over epsilon. And when you decrease the denominator and you leave the numerator as it is, then the number itself increases. That is to say, 1 over 1 over epsilon will be greater than 1 over capital N. So you can see here, when we decrease the denominator from 5 to 4, here we will get a greater number than 1/5. Because 1 over 4, 1/4 is greater than 1/5. So when you decrease the denominator, the number itself increases, and therefore 1 over 1 over epsilon is greater than 1 over capital N. Okay? And what is the value of 1 over 1 over epsilon? It is equal to epsilon. Okay? So we actually proved that if we choose capital N that is greater than 1 over epsilon, we will get that the absolute value of 1 over n minus the limit 0 is smaller than epsilon. That is to say, if we choose capital N that is greater than 1 over epsilon, then the condition that must hold indeed holds. And for that reason, we actually proved that for any epsilon that is greater than 0, there exists a natural number that is capital N, and we choose natural number that is greater than 1 over epsilon. And for any natural number n then that is greater than capital N, and we choose capital N that is greater than 1 over epsilon, we will get that the absolute value of 1 over n minus the limit 0 is less than epsilon. That is to say, if we choose capital N that is greater than 1 over epsilon, then the condition holds. And therefore, we actually succeeded to prove that the limit of sequence an that is equals to 1 over n when n tends to infinity is indeed equals to 0. Okay? Okay. So we finished to talk about sequences that have a limit that is a finite limit, because L is the limit and L belongs to the real numbers. And so in the next step we'll talk about sequences that has a limit in the broadest sense. Their limit is not finite but infinite limits. We talk about sequences that have infinite limits. That is to say, those sequences have a limit in the broadest sense. So the next topic is sequences that have infinite limits. So a sequence an is said to tend to plus infinity, and it is written that the limit of sequence an when n tends to infinity will be equal to plus infinity. A second way to write down the same thing is an with the right arrow equals to plus infinity. Okay? Those two expressions have the same meaning, and the meaning is that the limit of sequence an when n tends to infinity is equals to plus infinity. So this sequence has a limit in the broadest sense. Okay? So only if the following condition holds, you can say that the limit of sequence an in the broadest sense when n tends to infinity equals to plus infinity. And the condition that must hold is as follows. For every real number k, there is a natural number capital N, such that for every natural number n that is greater than capital N, we will get that an is greater than k. I repeat again. For any real number k as large as we would like, there exists a natural number n, a natural number capital N, and so for every natural number n that is greater than this capital N, we will get that an is greater than k. Okay, so that is to say, the terms of the sequence are eventually larger than any fixed k. Because of the fact that until the index n we have a fixed terms that might not obey to this rule, but we can neglect them. Why? Because from the index n until plus infinity, or the index from the index n onwards, we have infinite terms of sequence an that obey to this rule. That is to say, they are greater than k, that is actually a large number, as large as we want. And because of the fact that we have infinite terms of sequence an that are larger than k, for that reason, the limit of the BROADEST sense of sequence an when n tends to infinity equals to plus infinity. So symbolically, we will write down the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to plus infinity as follows. For every k as large as we want, k belongs to the real numbers, there exists, this is the sign of exist, and natural number capital N belongs to the natural numbers. So for every n that is greater than capital N, so for every natural number n that is greater than capital N, I will add here that n is also belongs to the natural numbers. For any natural number n that is greater than capital N, we will get that an is greater than k. That is to say, from the index n onwards, we have infinite terms of sequence an that are greater than k, and therefore, for that reason, the limit of sequence an in the BROADEST sense when n tends to infinity will be equal to plus infinity. Okay? So, in the next step, I will present to you an example of a sequence that its limit in the BROADEST sense is equal to plus infinity. That is to say, we will prove that the limit of the natural numbers when n tends to infinity, the limit in the BROADEST sense is equal to plus infinity. We can present the natural numbers according to this formula that an equals to n. So when the index n equals to 1, that is to say the value of the first term a1 will be equal to 1. So the value of the second term, so when n equals to 2, that is to say a2 will be equal to 2. When the index n equals to 3, that is to say a3 will be equal to 3, etc., etc. When the index n equals to 100, so the value of 100th term, a100, will be equal to 100. And finally, when the index n equals to n, so the value of an is n. So it is very easy to see here that the terms, as n increases, the terms of the set of the natural numbers are also increasing, and therefore we can, and there is no any limit to the to this increase, so we can assume that the limit of the set of the natural numbers when n tends to infinity, in the broadest sense, equals to plus infinity. Okay? So, in order to prove that the limit of the set of the natural numbers in the broadest sense is equal to plus infinity, we will have to prove that the condition that must hold indeed holds. So the following condition must hold in order that the limit of the set of the natural numbers in the broadest sense will be equal to plus infinity. So for every real number k, the condition that must hold, the following condition must hold in order that the limit of the set of the natural numbers will be, in the broadest sense, will be equal to plus infinity. The condition is as follows. For every real number k as large as we would like, there is a natural number that is capital N, and for every natural number n that is greater than this capital N, we will get that an is greater than k. An is greater than k. I repeat again. The condition that must hold is as follows. For every k as large as we would like, there must be a natural number capital N, and for every natural number n that is greater than capital N, we will get that an is greater than k. That is to say, from the index n onwards, we must have infinite terms of the set of the natural numbers that are greater than k. So, in order that this condition will be true, we will choose capital N that is equal to the integer value of k plus 1000 when it is rounded up. Okay? And the definition of the set of the natural numbers are defined according to this formula. An equals to n, and we have the right to choose n that is greater than capital N, and we have already choose capital N that is equals to the integer value of k plus 1000 when it is rounded up. So, from this inequality, we will derive that an is greater than the integer value of k plus 1000 when it is rounded up. So, if an is greater than the integer value of k plus 1000, let alone that an is greater than k. In conclusion, we can say that if we choose capital N that is equal to the integer value of k plus 1000 when it is rounded up, the condition that must hold indeed holds. Why? Because for capital N that is equal to the integer value of k plus 1000 when it is rounded up, we will get that an is greater than k. That is to say, from the index n onwards, we have infinite terms of the set of the natural numbers that are greater than k. That is to say, the condition holds. And for that reason, we actually proved that the limit of the set of the natural numbers, that is an equals to n when n tends to infinity, is indeed equals to plus infinity. Okay? So we finished to talk about sequences that have a limit in the broadest sense, and their limit when n tends to infinity is equals to plus infinity. In the next step, we'll talk about sequences that have a limit in the broadest sense, and their limit is equals to minus infinity. Okay, so here similarly we say that the sequence an, the limit of sequence an when n tends to infinity tends to minus infinity. That is the first way to write it down, and we can write down the same thing in a second method, an with the right arrow, and the limit equals to minus infinity. So those are the two methods to write down the same thing. To write down that the limit of sequence an when n tends to infinity in the broadest sense is equals to minus infinity. So only if the following condition holds, we can write down that the limit of sequence an, we can say that the limit of sequence an when n tends to infinity, the limit in the broadest sense will be equal to minus infinity. And the condition that must hold is as follows. For every real number k as small as we would like, there is a natural number capital N, such that for every natural number n that is greater than capital N, we will get that an is smaller than k. That is to say, the sequence terms are eventually smaller than any fixed k. Again, because of the fact that until the index n we have fixed terms, so we have maybe fixed terms that are not obeyed to this condition, but because of the fact that from the index n onwards, we have infinite terms of sequence an that are smaller than k. So we have infinite terms of sequence an that obey to this condition, and therefore we can say that the limit of sequence an when n tends to infinity in the broadest sense is equal to minus infinity. Okay, so symbolically we can write down that the condition that must hold as follows. For every k as small as we would like, k belongs to the real numbers. For every real number k as small as we would like, there exists, this is the sign of exist, a natural number capital N that belongs to the n belongs to the natural numbers, and for every natural number n that is also belongs to the natural numbers here. So for every natural number n that is greater than capital N, we will get that an is smaller than k. An is smaller than k. I repeat again that until the index n we have fixed terms, so may be fixed terms not obey to this condition, but from the index n onwards we have infinite terms of sequence an that obey to this rule, and therefore the limit of sequence an in the broadest sense when n tends to infinity will be equal to minus infinity. Okay. So we finished to talk about the topic of infinite sequences, and in the next term, or actually we finished to talk about the topic of infinite limits. We actually talked about sequences that have a limit in the broadest sense of plus infinity, and then we talked about sequences that have a limit in the broadest sense that is equal to minus infinity. In the next topic we will talk about the arithmetic of the limits. Arithmetic of limits. So if the limit of sequence an when n tends to infinity, if this limit exists, and also the limit of sequence Bn when n tends to infinity, it is also exists. So if the limit of sequences an and Bn exist, then the following equations will be true. according equation number 1 is true, that the limit of sequence an plus bn when n tends to infinity will be equal to the limit of sequence an when n tends to infinity plus the limit of sequence bn when n tends to infinity. So I will explain the meaning of equation number 1. According to equation number 1, here we have two sequences, an and bn. Both of them have a limit. So in the left side of equation number 1, we have, if we actually add the terms of the sequence an to the terms of sequence bn correspondingly, in this way we create a third sequence. In the next step, we will find out the limit of the third sequence that we created when n tends to infinity, and this limit must equal, in the right side of equation number 1 we have here, if we calculate the limit of sequence an separately, then we will calculate the limit of sequence bn separately, and then if we add the two limits, the result must be equal to the limit of the third sequence that we created here when n tends to infinity. So this is the meaning of equation number 1. And we have equation number 2 that is also true. According to equation number 2, the limit of sequence an minus bn when n tends to infinity is equals to the limit of sequence an when n tends to infinity minus the limit of sequence bn when n tends to infinity. So I will explain the meaning of equation number 2. According to equation number 2, in the left side of equation number 2, here we will, if we subtract the terms of sequence bn from terms of sequence an correspondingly, in this way we create a third sequence, and then we'll calculate the limit of the first sequence that we created, and the result must be equal to the left side of equation, to the right side of equation number 2. In the right side we have here if we calculate the limit of sequence an separately, then we will calculate the limit of sequence bn separately, and then if we subtract the limit of sequence bn from the limit of sequence an, the final result must be equal to the limit of the first sequence that we created here when n tends to infinity. Okay? And we also have equation number 3 that is true. According to equation number 3, the limit of sequence c times an when n tends to infinity must be equal to c times the limit of sequence an when n tends to infinity. We'll explain the meaning of equation number 3. In the left side of equation number 3, we actually find out the limit of sequence c times an. Here c is any real number. C belongs to the real numbers. So we'll find out the limit of sequence c times an when n tends to infinity, and the result must be equal to the limit of sequence c, the limit of sequence an when we will calculate it separately. And after we found out the limit of sequence an, we will multiply the result by c, and the final result must be equal to the limit of sequence c times an when n tends to infinity. And we have equation number 4 that is also true. According to equation number 4, the limit of sequence an times bn when n tends to infinity equals to the limit of sequence an when n tends to infinity times the limit of sequence bn when n tends to infinity. Again, I will explain the meaning of equation number 4. And equation in the left side of equation number 4, here if we multiply the terms of sequence an by the terms of sequence bn correspondingly. In this way, we will get a third sequence. Then we will find out the limit of the first sequence that we created when n tends to infinity. So the result here must be equal to what is written here in the right side of equation number 4. In the right side of equation number 4, it is written that here we will find out the limit of sequence an separately. We will find out the limit of sequence bn separately, and then we will multiply the two limits by each other, and the final result must be equal to the limit of the third sequence that we created here in the left side of equation number 4. And we have also equation number 5 that is true. According to equation number 5, the limit of sequence an over bn when n tends to infinity equals to the limit of sequence an when n tends to infinity over the limit of sequence bn when n tends to infinity, provided that the limit of sequence bn when n tends to infinity is not must not equal to 0. Why? Because it is not allowable to divide anything by 0, and if the limit of sequence bn when n tends to infinity is equals to 0, it will come out here that we are dividing the expression in the right side of equation number 5, in the denominator we will have 0. That is to say, we divide here this expression by 0. Okay, that is the reason it is not allowable that the limit of sequence bn when n tends to infinity will be equal to 0. So what is the meaning of equation number 5? Here we have actually here we will divide the terms of sequence an by the terms of sequence bn correspondingly. In this way we create a third sequence. Then we will calculate the limit of the first sequence that we created, and the result must be equal to what is written here in the right side of equation number 5. In the right side of equation number 5 we have here we will calculate, if we calculate the limit of sequence an separately, we will calculate the limit of sequence bn separately, and then if we divide the two limits that we got, if we divide the limit of sequence an that we got by the limit of sequence bn, the result must be equal to the limit of the third sequence that we created here when n tends to infinity. Okay, and finally we have also equation number 6. According to equation number 6, that is true, the limit of sequence an to the power of p when n tends to infinity is equals to the limit of sequence an when n tends to infinity to the power of p. So I'll explain what is the meaning of equation number 6. The left side of equation number 6, here we will calculate the limit of sequence an to the power of p when n tends to infinity, and the result must be equal to the limit of sequence an when we will calculate it separately, and after we found the limit of sequence an, we will raise this limit to the power of p, and the result must be equal to the limit of sequence an to the power of p when n tends to infinity. Okay, so in the next step I'll summarize the lecture. So in this lecture we talked about the limit of a sequence. So what I mentioned in the beginning of the lecture, a sequence is a set of numbers. A sequence could be finite, like this sequence that consists of only 3 terms, but a sequence also can be infinite, like the set of the natural numbers, this set that consists of infinite terms. In this lecture we talked only about sequences that consist of infinite terms. Actually, a sequence that consists of finite terms, it is not very interesting. It is not very interesting thing, because we know everything about that sequence. We know what is the first, the value of the first theorem, what is the value of the last theorem, what is the value of the seventh theorem, and so on and so on. Okay, but when we are talking about sequences that consist of infinite terms, then we have the challenge to find out the limit of those sequences. Okay? So we write down that the limit of sequence an and n tends to infinity is equal to L. L belongs to the real numbers. So here we are talking about a finite limit. So here n is the index of the theorem. That is to say, here when the index n equals to 1, the value of the theorem is 1. When the index n equals to 2, the value of the second theorem is 2. When the index n equals to 100, the value of the 100th theorem of the set of the natural number is equal of the set of the natural numbers is equals to 100. And a is the value of the theorem. Here, the value when n equals to 100, the value of the theorem is 100. So here we write down the limit of sequence an when n tends to infinity equals to L. So if a sequence has a limit, it must have only one limit. And then I know that that the sequence an is a convergent sequence. Why? Because it converges to the limit L. But if a sequence has two limits, then it doesn't have a limit at all. So if sequence Bn doesn't have a limit, then sequence Bn is defined as divergent sequence. Okay? So what is the definition of the limit of a sequence? Here we write down that the limit of sequence an when n tends to infinity is equals to L. L belongs to the real numbers. We can write down the same thing, like according to the second method, an with the right arrow is equal to L. The meaning of those two expressions is the same, that the limit of sequence an when n tends to infinity is equals to L. So the following condition must hold in order that the limit of sequence an when n tends to infinity will be equal to L. L belongs to the real numbers. That is to say, here we are talking about a finite limit. So the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to L is as follows. For every epsilon that belongs to the real numbers, that is a positive number, it is greater than 0, and is as small as you would like, that is to say it is very close to 0, but still it is greater than 0. So for every epsilon that is greater than 0, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that the absolute value of an minus L is less than epsilon. Okay? That is to say, until the index n, we have fixed theorems. So we will have in sequence an fixed theorems that are not obey to this condition. But because of the fact that from the index n onwards we have infinite theorems, that is to say infinite theorems, of sequence an obey to this condition, that is, the absolute value of an minus the limit n is less than epsilon. And because of the fact that we have infinite terms of sequence an that obey to this condition, for that reason we can say that the limit of sequence an when n tends to infinity is equal to L. So graphically we can describe it like in this drawing. Here, if L is the limit of sequence an when n tends to infinity, here this is the environment of L. The environment of L starts from L minus epsilon. N minus epsilon itself is not included, and ends at L plus epsilon. L plus epsilon itself is not included in the environment of L. So in order that the limit of sequence an when n tends to infinity will be equal to L, infinite times of sequence an must be in the environment of L. That is to say, infinite terms of sequence an must be located inside those two brackets. Okay, otherwise sequence an doesn't have a limit. Okay, so symbolically we can write down the condition that must hold as follows. For every epsilon that belongs to the real numbers that is greater than 0, there exists capital N that belongs to the natural numbers. So for every natural N that is greater than capital N, we will get that the absolute value of an minus the limit N is less than epsilon. Then I actually presented to you an example for a sequence that its limit is equal to 0 when n tends to infinity. Here we proved that the limit of sequence an equals to 1 over n when n tends to infinity is equal to 0. First of all, which terms this sequence consists of? When n equals to 1, the value of the first term a1 equals to 1. When the index n equals to 2, the value of the second term of this sequence will be equal to 1 over 2, that is 1 half. When n equals to 3, the value, when the index n equals to 3, the value of the third term of this sequence n equals to 1 over n is 1/3, etc., etc. And when the index n equals to 100, then the value of the 100th terms of this sequence is 1 over 100. This is to say it is 0.01. So it is very easy to see that as n increases, the terms of this sequence are getting closer and closer to 0. Why? Because the first term is 1, the second term is 1/2, the third term is 1/3, the other terms is 0.01, so the terms of the sequence are getting closer and closer to 0 as n increases. So we can assume that the limit of this sequence an equals to 1 over n, and that when n tends to infinity is equals to 0. But in order to prove that the limit of this sequence is 0, we have to prove that this condition holds. So we write down the condition that must hold. Here we wrote down that the condition that must hold in order that the limit of this sequence will be equal to 0. The condition that must hold is as follows. Every epsilon that is greater than 0, there must be capital N that belongs to the natural numbers. So for capital N that is greater enough, we get that for any natural number n that is greater than that capital N, we will get that the absolute value of 1 over n minus the limit 0 is less than epsilon. Okay, so this condition must hold in order that the limit of this sequence will be equal to 0. So actually here this inequality must be true. Okay, but the absolute value of 1 over n minus 0 equals to 1 over n. Why? Because when you subtract 0 from anything, it changes nothing. So you can cancel out 0, and we're left only with the absolute value of 1 over n. And because of the fact that n is a natural number, so 1 over any natural number, it must be a positive number. And we know that the absolute value of any positive number equals to the positive number itself. For example, the absolute value of 5 is 5. So the absolute value of the absolute value of the positive number 1 over n equals to 1 over n. So we can cancel the absolute value here, and we have to prove that 1 over n is smaller than epsilon. In conclusion, we have to prove that the inequality 1 over n that is smaller than epsilon, it is true. So here we will multiply this inequality by n, and we get that 1 is smaller than epsilon times n. Here we will divide this inequality by epsilon, and we will get that n is greater than 1 over epsilon. That is to say, this is the condition that must hold in order that the limit of our sequence will be equal to 0. Okay? So we have to prove that this inequality is true, that n is greater than 1 over epsilon. So, but we have the right to choose out the value of capital N. So we will choose capital N that is greater than 1 over epsilon, and therefore for any n that is greater than capital N, that is to say, from the beginning we will choose n that is greater than capital N. So therefore this inequality is true according to our choice, and we only choose capital N that is greater than 1 over epsilon. So from this inequality that is true according to our selection, according to our choice, we will derive from this inequality, we will derive that n is greater than 1 over epsilon. That is to say, we proved that the condition that must hold, that is to say, the inequality n is greater than 1 over epsilon, indeed is true. Why? Because this inequality is true, and from this true inequality we found out that we derived that n is greater than 1 over epsilon. That is to say, we actually proved that the condition that must hold in order that the limit of the sequence will be equal to 0 indeed holds, and therefore the limit of our sequence an equals to 1 over n when n tends to infinity will be equal to 0. Okay? But here, according to our choice, n is greater than capital N. You can choose n that is greater than capital N. That is to say, this inequality is true according to our choice. So here we divide this inequality by n, and we get that 1 is greater than capital N over n. Here we divided this inequality by capital N, and we found out that 1 over n is smaller than 1 over capital N. We have already found out that the absolute value of 1 over n minus 0 equals to the absolute value of 1 over n, and the absolute value of 1 over n equals to 1 over n. But here we found out that 1 over n is smaller than 1 over capital N. So we can write down this inequality that is true, because we exceeded from this inequality that is true, and we arrived to this inequality that is also must be true. So we can copy this inequality that is true here. That is to say, here 1 over n is smaller than 1 over capital N. So here then we focused on this expression 1 over capital N. So if we leave the numerator as it is, as 1, and then if we decrease the denominator from capital N to 1 over epsilon, and here we know that 1 over epsilon is smaller than capital N, that is to say, when we decrease the denominator from capital N to 1 over epsilon, then the original number itself will be greater. That is to say, 1 over 1 over epsilon must be greater than 1 over capital N, because when we decrease the denominator, the number itself will be greater. And the value of 1 over epsilon is equal to epsilon. So actually proved that if we choose capital N that is greater than 1 over epsilon, the condition indeed holds. That is to say, the absolute value of 1 over n minus 0 is indeed less than epsilon. Okay? And for that reason, actually, we proved that for every epsilon that is greater than 0, if we choose capital N that is greater than 1 over epsilon, then for every n that is greater than capital N, then here we will get actually n that is also greater than 1 over epsilon. And finally, we actually arrive to the conclusion that the absolute value of 1 over n minus 0 is smaller than epsilon. Here we actually arrive from this inequality that is true. We actually arrive to the conclusion that the absolute value of 1 over n minus 0 is less than epsilon. That is to say, when we choose capital N that is greater than 1 over epsilon, we arrive to the conclusion that the absolute value of 1 over n minus 0 is less than epsilon. That is to say, we actually proved that the condition that must hold in order that the limit of sequence an equals to 1 over n when n tends to infinity is indeed 0. Okay, I repeat again, the condition that must hold indeed holds, and therefore the limit of sequence an equals to 1 over n when n tends to infinity indeed equals to 0. Okay, so we finished to talk about sequences that has a finite limit. Then we talked about sequences that has a limit in the broadest sense, or we talked about sequences that have infinite limits. So a sequence an when n tends to infinity, the limit of sequence an when n tends to infinity will be equal to plus infinity. So either we can write it lim an when n tends to infinity equals to plus infinity. The second way to write down the same thing is an with the right arrow is equal to plus infinity. So only if the following condition holds, we can say that the limit of sequence an when n tends to infinity equals to plus infinity. The condition that must hold is as follows. For every k as large as we would like, and k belongs to the real numbers, there exists capital N. So for every natural number n that is greater than that capital N, we will get that an is greater than k. So that is the condition that must hold in order that the limit of sequence an when n tends to infinity will be equal to plus infinity. Okay? So here, what is the meaning of this condition? Actually, because of the fact that until the index n we have fixed terms, so we will have a fixed terms of sequence an that doesn't obey to this condition, but because of the fact that from the index n onwards we have infinite terms of sequence an that are greater than k. And because on this fact we can say that the limit of this sequence an in the broadest sense when n tends to infinity is equal to plus infinity. Okay? So symbolically we can write down the condition that must hold as follows: for every k as large as we would like, and k belongs to the real numbers, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than that capital N, we will get that an is greater than k. I repeat again, only if we have infinite terms of sequence an that are greater than k, can say that the limit of sequence an and n tends to infinity is indeed equals to plus infinity. And because of the fact that from the index n onwards we have infinite terms of sequence an, so here we get that if this condition holds, we will have indeed infinite terms of sequence an that are greater than k, and therefore the limit of sequence an when n tends to infinity is indeed equals to plus infinity. Okay. Then I presented to you an example of the set of the natural numbers, and the limit of the set of the natural numbers when n tends to infinity is equal to plus infinity. We have to prove it, so we can present the natural numbers according to this formula: an equals to n. When the index n equals to 1, then a1 equals to 1. The value of the term is 1. When the index n equals to 2, then the second term, a2, equals to 2. When the index n equals to 3, then the value of the third term, a3, equals to 3. When the index n equals to 100, then a of 100 is 100. Okay? So you can see that as n increases, the value of the terms of sequence an equals to n, that is the set of the natural numbers, also increasing. Therefore we can assume that the limit of sequence an in the broadest sense will be equal to plus infinity. Okay? So the condition that must hold in order that the limit of the set of the natural numbers when n tends to infinity will be equal to plus infinity is as follows: for every real number k as large as we would like, there exists capital N that belongs to the natural numbers, and so for every natural number n that is greater than that capital N, we will get that an is greater than k. That is to say, from the index n onwards, we will have infinite terms of the set of the natural numbers that are greater than k. So in order that this condition will be true, we will choose capital N that is equals to the integer value of k plus 1000 when it is rounded up. And here we know that an equals to n because that is the way that we can present, that is the formula for to present the natural numbers. So an equals to n, and for every natural number n that is greater than capital N, so n is greater than capital N according to our choice. So for every n that is greater than capital N, we have already choose capital N that is equal to the integer value of k plus 1000 when it is rounded up. So this inequality is true according to our choice. Okay, so from this inequality we can derive that an is greater than the integer value of k plus 1000 when it is rounded up. Okay, and if an is greater than k plus 1000, the integer value of k plus 1000 when it is rounded up, let alone that an is greater than k. Okay, so we actually proved that the condition that must hold in order that the limit of the natural numbers in the bordered sense will be equal to plus infinity indeed holds, and therefore the limit of the set of the natural numbers when n tends to infinity is indeed equals to plus infinity. The limit in the bordered sense, of course, it is equal to plus infinity. Okay. Then we talk about sequences that have a limit in the broadest sense of minus infinity. Okay, so we can say that the limit of sequence an when n tends to infinity equals to minus infinity. We can write down the same thing in another way. An with the right arrow that is equals to minus infinity. So those two expressions have the same meaning, that the limit of sequence an when n tends to infinity equals to minus infinity. So only if the following condition holds, we can say that the limit of sequence an when n tends to infinity equals to minus infinity. The condition that must hold is as follows. For every k, as small as you would like, there exists capital N. So for every natural n that is greater than capital N, we will get that an is smaller than k. Or in other words, from the index n onwards, we must have infinite terms of sequence an that are smaller than k. K is a small number, as small as we would like. And because of the fact that we have infinite terms of sequence an that are smaller than k, for that reason we can say that the limit of sequence an when n tends to infinity equals to minus infinity. Okay, so symbolically we can write down the condition that must hold as follows. For every k that belongs to the real numbers as small as we would like, there exists capital N that belongs to the natural numbers. So for every natural number n that is greater than capital N, we will get that an is actually smaller. An is smaller than k. Here I write down an is smaller than k. I repeat again, the meaning of this condition is that after the index n onwards, we have infinite terms of sequence an that are smaller than k. And k is a small number, as small as we would like. And because of the fact that we have infinite terms of sequence an that are smaller than k, for that reason we can say that the limit of sequence an in the broadest sense when n tends to infinity equals to minus infinity. Okay, then in the next step we talked about the arithmetic of limits. So here if we have sequence and the limit of sequence an when n tends to infinity exists, and the limit of sequence bn when n tends to infinity also exists, so the limits of sequences an and bn, they both exist, then equation number 1 is true, that the limit of sequence an plus bn when n tends to infinity equals to the limit of sequence an when n tends to infinity plus the limit of sequence bn when n tends to infinity. We have equation number 2 that is also true. The limit of sequence an minus bn when n tends to infinity equals to the limit of sequence an when n tends to infinity minus the limit of sequence bn when n tends to infinity. We have equation number 3 that is also true. The limit of sequence c times an when n tends to infinity equals to c times the limit of sequence an when n tends to infinity. We have equation number 4 that is also true. According to equation number 4, the limit of sequence an times bn when n tends to infinity equals to the limit of sequence an times the limit equals to the limit of sequence an when n tends to infinity times the limit of sequence bn when n tends to infinity. We have equation number 5 that is also true. The limit of sequence an over bn when n tends to infinity equals to the limit of sequence an when n tends to infinity minus the over the limit of sequence bn when n tends to infinity. and because of the fact that it's not allowable to divide anything by 0, and the limit of sequence Vn when n tends to infinity is in the denominator of this expression, therefore the limit of sequence Vn when n tends to infinity must not equal to 0. And finally we have expression number 6 that is also true, that the limit of sequence an to the power of p when n tends to infinity equals to the limit of sequence an when n tends to infinity. So here after we will find out the limit of sequence an separately when n tends to infinity, then we will raise it to the power of p, and the result, the final result, must be equal to the limit of sequence an to the power of p when n tends to infinity. Okay, thank you very much.